So welcome to Model 2 of our Applied Maths Modelling project for 2025, where the theme is populations. In Model 1, we had this differential equation, dp dt is equal to k times p. And it worked quite well for a short time, but then as the population grew and grew and grew, well, it went so high that the Earth couldn't possibly sustain it. We reckon the carrying capacity for the human population on the Earth is about 12 billion. Whereas this model here, the population just went up and up and up and up, kept on increasing all the time. And that's just not possible. Eventually you get to a point where there isn't enough water, enough food, enough space to sustain a population. So in Model 2, we're now going to use this idea of the carrying capacity called capital K. So don't be mixing up capital K with little k. So I want to modify this formula here. And this is how I'm going to modify it. I'm going to multiply that kp by a factor of 1 minus p divided by big K, the carrying capacity. Now let me think about that formula for a minute. When the population is very, very small compared to the carrying capacity, that's a very small number, close to 0. And therefore, that bracket ends up being 1. So you're back to model number 1, aren't you? But as the population grows, that number becomes more substantial. And as a result of that, you're going to be multiplying kp by a fraction less than 1. And of course, when p reaches k, that value there is 1. 1 minus 1 is 0. And as a result of that, dp dt is equal to 0. The population will no longer grow. So it'll reach a certain limit. So what I want to do is I want to solve that equation for p. And this is probably the hardest thing you're going to do in this particular project. So if you go to your notes, you can see there the equation dp dt in Model 2 is equal to kp times 1 minus p divided by big K. We call that the logistic equation. So I want to solve that logistic equation. So let's get to it. This is a little bit tricky. So it's a first order separable differential equation. So I'm going to put p's on the left and t's on the right. So I'm going to have dp over, slide that p down. There's another p inside the bracket, so I've just got to slide down the entire bracket. 1 minus p divided by big K. And that's equal to, slide the dt up. The k is already there. K dt. So I want to solve that for p. So I'm going to integrate both sides. So look at the left-hand side there. You want to integrate that with respect to p? Well, that's tricky. I'm going to have to do a little bit of treatment on that stuff at the bottom of the fraction. So let me go over to the other board and do a little bit of algebra to tidy that up. So what do I want to tidy up? I want to tidy up 1 over p times 1 minus p divided by k. In other words, I want to put it into a format where I can easily integrate it. I have no idea how to integrate that as it stands. So first thing, I'm going to multiply above and below by k to get rid of that little fraction on the bottom. It's going to be k times pk times 1 minus p divided by k. So all I did was multiply above and below by big K. So that's equal to k times p. Multiply the k inside that bracket. So I get k minus, big K's cancel, minus p. Right, so I got rid of that little fraction at the bottom of the fraction. Now I'm going to split that into 2 separate fractions. We call this partial fractions. Now this isn't on your Leaving Cert Maths or your Leaving Cert Applied Maths, but there is a technique in the algebra section on my platform of fast-paced maths. If you go to identities there, it'll show you how to do this technique. But look, you don't have to know how to do it, so it's probably the only thing that I'm doing in my project that's a little bit outside what we do on our course. But if I turn that in, I can turn that into the following. That's equal to 1 over p plus 1 over k minus p. So there's a technique to show you how to do that. But that is right, because if I add these two fractions, let me add them by getting a common denominator. My common denominator is p times k minus p. P into that leaves me with k minus p multiplied by 1. Plus, bracket in there leaves me with p plus 1. P's cancel, so you end up getting k over p times k minus p. So it is correct. But how would you do it? How would you work out that? Well, that requires a technique on partial fractions. But anyway, let me take that result now, that all this stuff here is equal to 1 over p plus 1 over k minus p. You see what I did there? I broke them into two simple terms. Each of them can be integrated. So let me get back to my integral now. So now this integral turns into 1 over p plus 1 over k minus p dp, and that's equal to k times dt. Right, so now it's integrable. I just integrate term by term. Use the natural log function to integrate them, so it's the log of p. It's the log of k minus p, but don't forget to divide by the diff of the function, which is minus 1. So I get minus log of k minus p. And that's equal to the right-hand side, kt plus c. Let me use my log rules. So that equals the log of p over k minus p is equal to kt plus c. Let me escape from logs. So p over k minus p is equal to e to the power of kt plus c. And remember, we did this before. So that's e to the power of kt by e to the power of c. And e to the power of c is just another constant. So I incorporate it into a single constant like a, capital A. So it's equal to a times e to the power of kt. Let me work out that constant a using some boundary conditions. For example, when t is equal to 0, when we start doing our survey, then the population is, well, we're using a starting population in our analysis in model 1 of 6.83 billion, but let's just call it P0 so we can generalize it a bit more. So the population is P0. So therefore, replace P by P0, P0 over K minus P0, and that's equal to A times e to the power of 0, which is 1. So your value of A is equal to P0 over the carrying capacity K minus P0, where P0 represents the starting population when we begin our analysis. Okay, continuing on. So I'm at this point here. I've got a value for A, but it's a bit bulky, so I'll just leave A there for the time being. And you know what solving a differential equation means? I want to write it down explicitly in terms of P. So I want to get P on its own. So P is equal to, slide the bracket up. So I get A times K minus P, e to the power of KT. Let's multiply out the right-hand side. So P is equal to AK, e to the power of KT, minus PA, e to the power of KT. Let me bring all my P's to the left-hand side. So I've got P plus PA, e to the power of KT, and that's equal to AK, e to the power of KT. Take out the P in common on the left-hand side. So I've got P times 1 plus A e to the power of KT is equal to a big K e to the power of kt. So now I've got P on its own. P is equal to a big K e to the power of kt divided by 1 plus a e to the power of kt. Right, I'm going to do a little bit of work on that. So let me try and tidy it up. So where am I now? I've got P is equal to, top is a big K e to the power of kt divided by, I'm going to take out that a e to the power of kt in common from the bottom. So it's going to be a e to the power of kt times itself is 1 plus 1 over a e to the power of kt. So in other words, if you multiply that out, you get that exactly back. So that's equal to, I can do a bit of cancelling now. So the a e to the power of kt's cancel. So now I've got k over 1 plus, let me bring that e to the power of kt up to get e to the power of minus kt divided by a. So I've got a 1 over a there. Well, actually, let me turn that into a b. So finally, I'm going to end up with p is equal to k over 1 plus b times e to the power of minus kt. There's my solution. And what is b? Where b is, well, it's 1 over a, isn't it? And what's a? Well, let's go back to the previous board where I did have the a. So I got it here. So a is p0 over k minus p0. So 1 over a is that turned upside down. So therefore, b is equal to k minus p0 divided by p0. There is the solution to my differential equation in model number 2. And let's see, does that give me better results than the solution that I had in model number 1? So the next part in our notes, it says, using this model that we've just solved, show that the population will be at its carrying capacity of 12 billion as time goes to infinity. So there's my model 2 solution written down. We're talking about time going to infinity. There's a symbol for infinity. So therefore, what will the population be? The population P will be K. Well, what's our carrying capacity? That is 12 billion. So it's K divided by 1 plus B times e to the power of, so T is infinity. Multiply that by K. Well, it's still infinity. So I get minus infinity. And what can I say about e to the power of minus infinity? Well, e to the power of minus infinity is equal to 1 over e to the power of infinity. E to the power of infinity, well, that's an enormous number. E is about 2.718. So that number to a very, very high power, that number becomes enormous. 1 divided by an enormous number, well, that number tends towards 0. So therefore, as t goes to infinity, that number tends towards 0. So therefore, that there is equal to k. And k is the carrying capacity. So as time gets bigger and bigger and bigger, we never break through the barrier of the carrying capacity, which in this case is 12 billion. So the model works well so far in that instance. We're not going to get over a carrying capacity of 12 billion in model number 2. So let me further test my model 2 solution. They're saying in the year 2100, what will the population be? Remember in Model 1 we got 25 billion for that. That there is 9 decades after our starting point, so therefore t is equal to 9. And that number, 25 billion, of course, was way off, and that's why we have this new refined model. So let's see what we get when we do it with this new, better model. So there's my solution. In the year 2010, t is equal to 0, and the population there was 6.83 billion. So that was in our table of results. The year 2100, t is equal to 9, 9 decades after that. What is the population? We know the estimate of the carrying capacity for the Earth's population is 12 billion. And you see that value of k? I'm going to use that value of k from Model 1. We got 0.144. So the first thing I want to do is work out my value of b there. So b is equal to k, that's 12, minus p0, 6.83, divided by p0, 6.83. So let me go to my calculator. So fraction, I've got 12 minus 6.83 divided by 6.83. Execute. Turn that into a decimal format. Decimal. And I get, say, 0.757. So let me use that value. So my value of b is 0.757 to 3 decimal places. So now let's use this formula here to work out the population. In the year 2100, so p is equal to k, which is 12, divided by 1 plus b times 0.757, e to the power of minus little k 0.144 times t, and t is 9 decades after our starting point by 9. So let me put that into my calculator and see what kind of population that I get. So I've got fraction, 12 on top, divided by 1 plus b, which is 0.575, 757 should I say, multiplied by e to the power of minus 0.144 multiplied by t, which is 9. Execute that, and I get about 9.94 billion. That's okay. That sounds good. So after about 9 decades, 90 years, the population has reached 9.94 billion. The UN estimates it's probably going to be around 10.2 billion. So I think our model is working quite nicely. It's certainly a great improvement on model number 1. Finally, let me generate a graph over a long time. I'm going to go 50 decades. 50 decades would be 500 years. My formula is p is equal to k times, k is 12, over 1 plus b, we worked out b to be 0.757, e to the power of minus k, which I'm taking to be 0.144, times t. So I want to generate a graph from t is equal to 0, which is 2010, to t is equal to 50, which is 50 decades, 500 years beyond that. Now, I don't want to draw that graph myself. I'll be here all day generating the results. So I want you to use a little bit of software as well in your project. And I'm going to use something called Wolfram Alpha. So that's freely available. Just type in your Wolfram Alpha into Google and the free version of it will come in. And when it opens up, the very top box, I want you to put in that equation there. There's a little maths equation editor to do that, or you can use the code that I've given in the notes as well if you just want to copy and paste that in there. So let me have a look at what Wolfram Alpha will do for me. So there's my Wolfram Alpha, and there's my equation typed in, and I'm going to play that now. And what kind of graph does it give me? There's the graph that I've got. It starts at 6.83 billion, and then over 50 decades, you can see that the graph flattens out. It never gets beyond 12 billion. So that's exactly what our model predicted. It never goes beyond the carrying capacity. So if I was to sketch my graph, which you will put into your project, there is a limit of carrying capacity of 12 billion. So if I draw that horizontal line across there, my graph starts at 6.8, about there. And so over my 50 decades, my graph goes like this, and it kind of hugs that carrying capacity 12 billion, but never quite reaches it. Right, so that's model 2. That is a pretty good prediction of how the Earth's population behaves.